Good morning everyone, and welcome to today's worked exam answer video. Today I am taking on an acids and bases question without focusing on buffers. Today we're focusing on two different strong acids and a weak acid. First of all, we're thinking about diluting a strong acid and being able to work out the pH post dilution. Then we're thinking about a weak acid, and we've actually been asked to calculate the Ka value as opposed to the pH that we would normally be calculating. And then finally, we're taking a different strong acid and we are neutralizing it with an alkali, and we've got to work out the pH of the solution formed by figuring out which of those two substances is going to be in excess and thus get the pH from there. As always, I am going to be highlighting and annotating the questions, and I'm going to use my trusty red pens for my strong acids, my orange for my weak acid, and purple for my alkali. I can't help myself, I'm very sorry. And then I will obviously do all my worked answers and explain those as clearly as I can for you all. Okie dokie, so first up we have some hydrochloric acid, and the first thing that I tend to do with any acid or alkali calculation is write the dissociation. So because hydrochloric acid is a strong acid, it will completely dissociate into H plus and Cl minus ions, and you'll see why that's helpful in a moment. So we're given a 25 centimetre cube sample of a 0.085 mole per decimetre cubed hydrochloric acid solution. That was placed in a beaker, and then 100 centimetres cubed of distilled water were added. We have to calculate the pH of the new solution formed and give our answer to 2 decimal places. Now, anytime we do a dilution calculation, we have to work out the original moles of the substance. Then we can work out what the new volume has become, and then use the moles that we just worked out and the new total volume to get the new concentration, and then do whatever we need to do from there. And this is no different. So the first thing that I did was calculate the original moles of the HCl using the 0.0250 decimetre cubed volume and the concentration, and that gave me 2.125 times 10 to the minus 3 moles. Then I had to read the question really carefully, and they will do both of these scenarios in various questions. We're starting with 25 centimetres cubed here, and 100 centimetres cubed of distilled water were added. That means the new total volume is those two added together. Sometimes it will say that we start with 25 and we make it up to a total of 100, which isn't what we've done here. So we do need to figure out which of those two scenarios we're working with. Here we've got to add them together because it says 100 centimetres cubed of distilled water were added. That gives me a new total volume in decimetres cubed of 0.125, which I've took my moles, divided it by the new total volume, and that gave me my new concentration of my hydrochloric acid. Now, this is where knowing that hydrochloric acid is a strong acid is really important, because if I've just worked out the concentration of the HCl and all of that is going to dissociate fully into H plus and Cl minus ions, I also now have the H plus concentration because it is the same as the HCl concentration for that reason. So my H plus concentration is 0.017 mole per decimetre cubed, and then once we've got the H plus, we can get our pH by calculating minus log base 10 of that 0.017 and to 2 decimal places. That gives me a pH of 1.77. First part done. For the second part, we've moved on to HX, which is a weak monobasic acid. So as soon as I knew that HX was a weak acid, again I wrote my dissociation. Because weak acids only slightly dissociate in water, we need our reversible arrow, because we're going to end up with an equilibrium mixture of all three of these things, HX being the weak acid and then the H plus and the X minus. We've been asked to write an expression for the acid dissociation constant Ka, which is another reason why this is helpful, because Ka is the concentration of the products divided by the concentration of the reactant. So we've got square brackets concentration of H plus, square brackets for the concentration of X minus, and then square brackets for the concentration of HX. Now, please do not simplify the Ka expression here. As we're going to see in the next part of the question, we can simplify the top line to say H plus squared, because every time one molecule of HX dissociates, we make the H plus and the X minus in a 1-to-1 ratio. So rather than having two unknowns, we simplify it to say H plus squared, so we then don't have two unknowns in our expression. However, if you were to write the Ka expression like this, up here, you wouldn't get the marks. So please always write it in full whenever you are asked for a Ka expression. You can then simplify it as you go on to do your calculation. Now, this particular calculation is slightly different. Rather than giving us the value for Ka and us having to rearrange that expression to get the value for the pH, they've actually given us the pH as 2.79. They've also given us the concentration of the HX solution as 0.085. We therefore don't actually need to rearrange our Ka expression, but what we do need to get is a value for H+. We have the concentration of HX, but we do not have the concentration of H+. However, because we have the pH, we can work out H+ concentration by doing 10 to the minus pH. So 10 to the power of minus 2.79, which gave me 1.62 times 10 to the minus 3. That I can then square, and then I can divide that by 0.085 and give my answer to three significant figures as requested for the Ka value as 3.09 times 10 to the minus 5 mole per decimetre cubed. And then finally on to the last question. So we've been given 25 centimetres cubed of a 0.620 mole per decimetre cubed solution of nitric acid. That was placed into a beaker, and then 38.2 centimetres cubed of 0.550 mole per decimetre cubed sodium hydroxide solution were added. And we have to calculate the pH of the solution formed and give our answer to 2 decimal places. They then go on to give us the ionic product of water Kw, which is 1 times 10 to the minus 14 at 25 degrees. Now that is a huge clue. We would not need a value for Kw if the nitric acid was in excess. Likewise, if they had both completely neutralised each other and there was none of either left over, we would not need Kw. However, if the alkali is in excess, we need Kw, because when we work out the pH for our alkalis, we get the OH minus concentration, and it always comes back to the H plus concentration when it comes to working out pH, and it's the Kw expression that enables us to convert our OH minus concentration into a H plus concentration so that we can get pH. Now, AQA are pretty decent in that they don't tend to give you numbers that you do not need. So this cannot be a red herring, or it has never previously been a red herring. If you are given Kw, you will need to use it. So hopefully we establish that the sodium hydroxide is in excess. Now, please do not assume that these substances will react in a 1-to-1 ratio, because if we were to use sulfuric acid, that would be incorrect, or if we were to use barium hydroxide for our alkali, that would also be incorrect. Do not take the chance. Please write a balanced chemical equation. So nitric acid, HNO3, reacts with sodium hydroxide, NaOH, to make a salt plus water, which is sodium nitrate and water. And that is already balanced. So yes, whilst this is a 1-to-1 ratio between my acid and my alkali, it won't always be. Then I calculated the moles using the volumes converted into decimetres cubed times by the concentrations, and we can see that the alkali is in excess, because when the two substances are in a 1-to-1 ratio, we're just looking for the bigger number of moles. So yep, my alkali is going to be in excess. Happy days. I then need to work out how much alkali is left over once it has reacted with all of the nitric acid. So the nitric acid will be all reacted away, but we will be left with 5.51 times 10 to the minus 3 moles of the sodium hydroxide once we have taken away the 0.0155 moles that reacted with the nitric acid. Now, it's really important that we know that this is now the moles of sodium hydroxide remaining. Some students use this as the concentration. It is not. This is the excess moles. So now we need to work out the new concentration by using the moles divided by the new total volume. Again, new total volume because we now have the volume of the acid and the volume of the alkali in the beaker. So I added those together. Moles divided by that value gave me my new concentration. Now this is both the new concentration of the sodium hydroxide and the concentration of the OH minus ions. Why? Because sodium hydroxide is a strong alkali, and strong alkalis, like strong acids, fully dissociate into their ions. So if I know the concentration of the NaOH, I also know the concentration of the OH minus because they are the same. From there, I need to use my Kw expression. So Kw is equal to the concentration of H plus times the concentration of OH minus. So if I rearrange that to get H plus, because that's what I'm going to need to get pH, we get Kw divided by the OH minus concentration. The Kw value was given, 1 times 10 to the minus 14, and we have the OH minus concentration now as 0.0872. Dividing those gives me a H plus concentration of 1.15 times 10 to the minus 13, and then if I do minus log base 10 of my answer for the H plus, I get a pH to 2dP of 12.94, which makes a lot of sense when my alkali is in excess, because that is a value that would suggest I have strong alkali in excess. Those calculations are tricky, and when you are left with the alkali in excess, you do get more marks because you have to convert between the OH minus concentration and the H plus concentration via the Kw expression to get pH. They are tricky, but if you follow a standard layout like the one I've used here, the steps are always the same. As with all calculations, once you know how to do it, it's a case of looking at what information you have, what it's asking you to calculate, using the same expressions that we usually would, subbing in our values and getting our answers, and the skills are the same every time. So my advice with acids and bases, as with all calculation based questions, is practice, 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 because I do appreciate that it's hard sometimes to know which type of calculation to apply to each type of question, but again, that's where it comes down to knowing things like what is a strong acid, what is a weak acid, strong alkali, and what sort of expressions we need to be using in each case. If anyone has any questions about any of these answers, please do leave me a comment. I am very happy to assist. Wishing you all a really fabulous day, guys. Thank you so much for watching.